Hello again everyone, welcome back to ptet.chemistry channel. So in this restructured tutorial, I'll go through this A-Level 9701 for the Cambridge International A-Level Chemistry exam. This is the June 21, the summer 2021 series. It's a paper 2, variant 2, meaning to say it's an AS component paper, which is suitable for many 16 to 18 years old chemistry students all around the world. So before I start, don't forget to click the button on the bottom right. So those are existent for all the YouTube tutorial videos. This is just to subscribe to the channel, to support the channel, and yeah, to get notified of all future videos. Also, please don't forget to actually share the channel widely with all your friends, chat group, juniors, seniors, teachers, relatives, whoever else you think the channel might be useful for. Okay, so do follow me at ptet.chemistry. So against the watermark, there is the various social media platforms: Facebook, Instagram, and Twitter. So you can choose whichever one you like to use, and do stay connected and send in questions, send in queries, and I look forward to hearing from you. Let's get started with this question number 1. So group 2 metal combines with bromine to form a crystalline solid. So you have a group 2 metal, meaning to say it's going to be a divalent cation when you form the ionic compound with the bromine, because metal and non-metal, such that you have M2 plus and Br minus. You need 2 of that Br minus. That's why the formula is 1 of the M and 2 of the Br. So that equation is balanced as such, and then we add excess aqueous silver nitrate. So silver nitrate is going to react with it's going to take out the bromide ions from the group 2 bromide, and you get a precipitate. Not surprisingly, that is your silver halide, that is your silver bromide precipitate, and in doing so you will get the group 2 nitrate, because again you have M2 plus being a group 2 cation. They want to complete the outer shell when they form the cation, so they lose the 2 outer shell electrons. You also have NO3 minus, which is the salt that you get from nitric acid. So nitric acid is HNO3, so you're going to get 2 of the nitrate, because the charges of the anions need to balance out the charges of the cations. There's the very essence of bonding, because the ionic compound that you're forming doesn't have any overall charge. So it is this precipitate that you're forming, and we're going to have balanced equation whenever you do equations. So you're going to have 2 of that and 2 of that. So this is your balanced equation now. This precipitate is dried, and the mass of the precipitate is recorded. The formula and the color. So part A, they try to give you a lot of free marks here. So the formula is the easy bit here. So it's silver bromide. As you know from your paper 3 practical case study, a test for bromide ion is when you add a little bit of nitric acid to get rid of any carbonate that might be present, and then what you will do is you will add some silver nitrate aqueous solution, and you get a cream precipitate. And this cream precipitate will not dissolve in dilute ammonia, in excess dilute ammonia. It can only dissolve in concentrated ammonia, unlike silver chloride, which can dissolve in excess dilute ammonia. They're asking us to complete the equation, which I have done. So I am just going to copy paste whatever I've done on top there, and copy it in this space down here. And there's the balance equation there. So they have given us MBR2 in front, so perhaps I can follow their order, since this is actually trying to replicate the question paper itself, which of course I can't be showing anymore as a result of copyright stuff. From a balance equation, you should be able to do some mole calculations. So we are given 0.250 gram of MBR2, so we have 0.250 gram, and we have what do we have? We have 8.415 times 10 to the power minus 4 mole of this MBR2. So we need to work out the relative formula mass of these. So this is for MBR2. So given the mass and given the mole, so you can hopefully see that mass equal to mass over MR equal to mole. I don't know what I was doing there. Okay, so you have 8. I should probably rearrange my equation first, because based on what I said previously in all my previous tutorial, it's very important to rearrange first before you do anything. So your MR is going to be 0.250 over 8.415 times 10 to the power minus 4. So now we're ready to just key in our calculator. 0.250 divided by 8.415 times 10 to the power minus 4. I'll probably delete this. Nah, it's alright. Okay, I'll just move this up a little bit on the side so I get a bit more space there. The beauty of working on the screen is I get the luxury of doing all these things. They don't tell us how many significant figure, but based on the information given, if you see 1, 2, 3, and 4 significant figure, and the 250 is 3 significant figure, I would say anywhere between 3 and 4 significant figure, you would have been alright, because there would have been appropriate number of significant figure. So my MR I can say is going to be, if I do that to 3 significant figure, 297 gram per mole. So this is 3 significant figure. Okay. So I guess that's the part 1 of that question, which is identifying the MR, and then second bit is identifying the metal M. Remember, M is a group 2 metal, as stated in the question earlier. So it's a group 2 metal, and we know the molecular mass for the 2 bromine from the periodic table. So your MR is 297, and you have MBr2. So I have the AR of M, and I have the relative atomic mass of bromine. From your periodic table, bromine is element number 35 in group 17, so that's 79.9 times 2 for the 2 bromine atom there. So the relative atomic mass of M is 297 minus 79.9 times 2 is 159.8. 297, take away that, I get 137.2. Look at group 2 metal, 137.2, 137.3, therefore M is equal to barium. So you could write barium, you could write the symbol Ba. I don't think you will get penalized for it. Barium, when they form compound, it will be Ba2 plus Br minus, such that you get Ba, Br2. You got to show your working, unfortunately. If you don't show your working, you just give the answer, even they are correct, you might lose the mark on the working, because the question specifically says show your working. All right? Part D, so question 1, part D, we are supposed to look at observations. So we have MBr2. Doesn't matter whether you identify it as barium just now or not, but you know when it dissolve in water, what will happen is, well, they just say it just dissolve in water, so I guess you get M2 plus aqueous, and you just get Br minus aqueous, so they just dissolve without doing anything. And then you bubble chlorine gas through the solution. This is a bit of group 17 chemistry. This is to do with the oxidizing power of the halogen. So the oxidizing power of the halogen, chlorine is a stronger oxidizing agent than bromine than iodine. Meaning to say they like to get reduced, because oxidizing power means ability as an oxidizing agent. And if you think about it, what is an oxidizing agent? An oxidizing agent oxidizes the other substance. So it oxidizes other substance. And what happened to itself? Itself get reduced. So itself would gain electron, because if you think about the acronym, well, RIC, so itself gain electron. So whenever you're asked to think about the definition of, the definition of oxidizing or reducing agent, do not try and get to the final stage without going through the motion, which are the thought processes. I've never remembered this. I always remember what it does, what happened to itself, and from there I just need to recall back what oxidation and reduction means and all that kind of thing. So chlorine is a stronger oxidizing agent than bromine, which means that chlorine gas can oxidize the bromide ions which are present in the solution. So what observations will I see? The color of chlorine gas, chlorine is color, by the way, it's kind of like pale green gas. And as the chlorine reacts, then the pale green gas will disappear in color. It will get lighter, or the color will fade. This is a reddish brown liquid. But of course here we have reddish brown, don't know why I can't spell that properly. Reddish brown liquid as a pure substance, but when you dissolve Br2 in water, it's gonna look a bit like orangey yellow, much more dilute. Whereas iodine is a dark gray solid at room temperature and pressure. They've asked us to describe what you will see, but instead of describing, I'll first write down an equation on what I would expect. Okay, so let me just start by Br minus plus Cl2. What I'll get will be Cl minus plus Br2, because chlorine is a stronger oxidizing agent than Br2, so chlorine can oxidize Br minus 1 to Br0. So talking about oxidation state, actually before that, I must balance my equation with the number of atoms correctly balanced and the charges. -1 times 2 is -2 overall on the left, -1 times 2 is -2 overall on the right. Equation is balanced now. I can talk about my oxidation number. Oxidation number of bromide follow the charges on the ion. Oxidation number of an element, because they're bonded to themselves in this diatomic molecule, is just chlorine 0. Chlorine is -1 oxidation state in this chloride ion following the charges, and Br is again 0 in the diatomic molecule, which is how the element exists as. So we can see that the chlorine acts as an oxidizing agent. It oxidizes Br -1 to Br 0, so that is your oxidation. So these are not our observations yet, okay? So chlorine 0 to chlorine -1 is your reduction. In terms of observations, they're just looking to see what actually happened, but it's really to think about what really happened. If you know the equations, you can think about what you would expect to see based on what we know about the color of the halogens. So the bromine will be produced and they are in solution because this was dissolved in water. So Br2 will be produced, meaning to say we will see, first of all, the pale green color of the pale green color of the chlorine gas, because that's what the question say, will get lighter, meaning to say the color fades. Okay, it gets lighter and lighter until eventually it's used up. And then what also happened is this thing is also colored, but in water it's not going to be this reddish brown liquid, which is dark color. So perhaps you will see an orange yellow solution. The solution turns orange yellow because there's the color of aqueous bromine. Of course, depending on the intensity or the concentration of the Br2 in the water, then that is going to affect how much intense this color is. It could get to a bit darker, but most likely it won't go to this reddish brown color unless it is just pure Br2 without any water. So what is this type of reaction? So D part 2. So I talked a lot about this observations thing, but there are actually very, very important reactions in the context of group 17 chemistry, in the context of oxidation and reduction. So this reaction is definitely called a redox reaction because there's oxidation and there's also reduction in the same reaction. Part E. So part E is still the same question. They say Y is an insoluble solid. So Y is insoluble. It is insoluble solid. It has halide. Halide meaning could be the chloride, bromide, iodide. We don't talk about fluoride because that's not part of your group 17 chemistry in AS syllabus. But doesn't mean that you don't call fluoride halide. Fluoride is actually a halide as well. A single reagent is added to it to determine the halide ion. What is this single reagent? Just adding one reagent and you can tell the identity. You can identify the halide ion. So this is your paper 3, test for halide ion, test for chloride, bromide, or iodide, and this reagent has to be what we have done earlier, which is this aqueous silver nitrate, or you can just say AgNO3 bracket aqueous. That will have been perfectly all right. Now they say confirm that it contains bromide. Confirm it contains bromide. So you get a cream precipitate because there's the color of silver bromide. Silver iodide is, don't know why that T doesn't spell properly. Cream precipitate forms. So a silver chloride will be white precipitate. Silver iodide will be yellow precipitate. Silver bromide is your cream precipitate. So question 1, part F. We have separate 1.0 gram samples. We want to identify anions. So these kind of questions are very clever these days. They don't ask you as much in your paper 3. They move a little bit of these qualitative analysis into the theory paper. I don't know why. Perhaps it's because because of COVID, then not a lot of students actually get to do practical. So in light of that, they might actually skip the practical paper, and they might actually in turn move a little bit of those qualitative analysis stuff into theory paper. paper, which of course the qualitative analysis table will never be given in a theory paper, not in paper 1, 2, 4 or 5. So students are expected to be able to do and basically to remember that whole analysis which they will have done in a normal theory setting as part of the syllabus. Okay, so here you want to identify anion, but you want to use action of heat. So what we are going to do is thermal decomposition. So each of these perhaps can be thermally decomposed, so we will see what actually happened there. For 3 marks and a lot of lines, you are supposed to identify MgCO3 versus MgNO3 twice versus MgO. So the carbonate, the nitrate and the oxide. So first of all, I'll say that MgCO3 decomposes under heat to give me MgO plus H2O. Sorry, not H2O, what am I talking about? CO2, because it's decomposition of carbonate. So bubble the gas, not really bubble, pass the gas, because there's no water, how can there be bubble? Pass the gas produced during this thermal decomposition. So you're going to produce carbon dioxide gas, and the MgO is a solid, so there's a solid during this thermal decomposition. So you're testing for carbon dioxide gas, so you pass it through lime water. But of course they say, how can you tell the difference? So as you pass it through lime water will turn milky or cloudy because it will form calcium carbonate, as the lime water is calcium hydroxide reacting with carbon dioxide will give you a salt, which is calcium carbonate. As you know from O-level or IGCSE chemistry, the group 2 carbonate is insoluble. In fact, you also learn it from AS chemistry as part of group 2 chemistry. So this is your base, which is your lime water. Saturated solution of lime water is calcium hydroxide. There is your acidic oxide. What you're going to get is calcium carbonate, which is insoluble. All the group 2 carbonate is insoluble, and therefore they crash out as a milky or cloudy or white precipitate. On to the second one, so you have magnesium nitrate. This is a lot easier because the gas will be colored. So as you decompose, you're going to get magnesium oxide, NO2 gas, and NO2 gas. We have 2 nitrates, so we get 2 NO2, and we have 1 oxygen, and we have 4 oxygen, so 5 oxygen. We have 6 oxygen there, but we have oxygen molecule, so we just need to put a half in front of that. So oxygen gas itself is colorless. Okay, oxygen gas itself is colorless, but what happened with NO2 is that it's a brown gas. So what we can see is as this reaction progresses under heat, because you're going to heat it, so this delta refers to heat, a brown gas is observed. A brown gas is observed, or a brown gas forms. So that confirms the identity of the nitrate there. Last but not least, you wouldn't get anything really. So the MgO doesn't decompose, so no decomposition. So meaning to say you can collect the gas, so no observable change. In fact, if you compare with number 1 where you just hit the carbonate, there'll be no observable change as well because it's white and white. But I can say I can collect the gas. We can collect gas which is not formed. Okay, so we can test with lime water. So I'm just simply stating a test, which if it is colorless, you can't see it, you don't know whether there is CO2 or not, so you just collect the gas. If it is formed, it will turn lime water milky. Here it is not formed, so we can test with lime water. No CO2 produced, therefore lime water remain colorless. It remains a solution. Lime water remains colorless solution. So this question is asking you, how can you identify? Okay, so you cannot stop by saying no change, because what does no change mean? Can you see white versus white? You can't tell there's CO2 because it's colorless unless you actually test for the gas. So you have to collect the gas here and collect the gas here, but of course here there's no decomposition, so no gas, so the lime water is just going to remain colorless solution, not a liquid but a solution, because calcium hydroxide is an ionic compound that's dissolved in water to give you a mixture, which is a solution. Okay, I hope that makes sense then. So this one is done. So we're still on question 1. So question 1F part 2 is about electronic configuration. If you look at the question, they say the magnesium cation in this salt. So the magnesium will form exclusively magnesium 2 plus to get a fully filled outer shell in all of this salt. You get Mg2 plus CO3 2 minus, Mg2 plus NO3 minus, that's why you need 2 of them, Mg2 plus O2 minus. So Mg2 plus will have lost 2 electrons from the magnesium atom, such that you get the same electronic configuration as neon, which is a fully filled second shell, well, up to second shell. So they don't have the 3s2 because you have lost the 3s2 electrons. So lost 2 electrons from 3s2. Question 1, part G, this is the end of this first question. What are they trying to do here? They are trying to distinguish, so MgCO3 versus MgOH twice, which is hydroxide. So this is a carbonate, this is a alkaline solid, is a basic solid, is alkaline. Add a small amount of each solid to HCl. So what is the similarity? What is the difference? First of all, the MgCO3 will react with HCl, and there you will get metal carbonate plus acid. You will get metal salt. This is straight from your lower secondary science or your year 9 chemical equations in terms of the general reactions. You get metal salt plus CO2 plus H2O. Whatever you write has to be balanced. So I've got 2 chlorine there, so I need 2 HCl, 2 hydrogen there give me H2O, the CO3 give me CO2, so that's all right there. Let me write the equation for what happened with magnesium hydroxide plus HCl. So this is your base or your alkali, this is your acid, this is going to be neutralization. Acid-base neutralization will give you salt, MgCl2 because Mg2 plus Cl minus, and it also give you water as well. Whatever equation you write has to be balanced every single time. So what's going to be the similarity and difference in these two reactions? I can say that from these examples, from these equations that I've shown above, in terms of the similarity, both reacts, both MgCO3 and MgOH twice react with HCl to form metal salt, which is MgCl2, same metal salt, and also H2O. What is the difference? The difference is obviously the carbonate also give you the carbon dioxide gas. So these are in solution, so you see bubbles or effervescence as this reaction progresses and give you a gas, but there's no gas given out here, so there's no bubble at all. So only the magnesium carbonate reaction gives bubbles or effervescence because CO2 is produced, CO2 forms in solution, whereas no such observation, no bubble, no effervescence, no such observations. What's wrong with my handwriting? Observations with the MgOH twice, basically the magnesium hydroxide, have no such observations. So that's the end of that 60-mark question. Pretty long for first question. Anyway, doesn't matter. Question 2. So question 2 looks like they start off on the states of matter. So they want you to give the formula of the particles. So they say the particles in solid lithium sulfide. So you need to know from the name itself what it means. Lithium sulfide, the formula given is Li2S. So hopefully you can see it's Li plus and S2 minus. You actually need 2 of that Li plus, so that is 2 times of the cation and 1 time of the S2 minus to get to a stoichiometric compound with no overall charge. So the particles that you want will be Li plus and also S2 minus. From the formula, a lot of students will just write down Li and S and they will be wrong because you don't have the atoms. You have the ions in this solid ionic compound there. That's first part. The second part is asking you about high melting point. So melting point is always to do with structure and bonding. You see there are 2 marks to this question. They say in terms of the structure. They don't talk about bonding, but you must always associate the two together. What is the structure and what bond are you breaking? That's why there are 2 marks to it, okay? So Li2S, as you can see, consisting of oppositely charged ions. So that one has a giant ionic lattice structure. So ionic structure is a giant lattice, so it's a giant ionic lattice structure. If you don't like the word lattice, you can just ignore it, but sometimes question does ask you what it meant by lattice. So giant ionic structure means melting. When we melt Li2S, what are we breaking? We need to break strong ionic bond. Ionic bond is the electrostatic force of attraction between the oppositely charged ions. In this case, it's between the Li plus and the S2 minus ions, and these are all stated in the syllabus as part of the states of matter topic under structure and bonding as well. So question 2, part B, is about what is meant by a coordinate bond. Coordinate bond has another name in the syllabus, in the curriculum. This is also known as dative covalent bond. So I personally like to use the term dative covalent bond, but because the syllabus does say coordinate bond is also used interchangeably with these, so they could ask you either, because they did state in the syllabus, it might just be you who didn't cover through the entire syllabus on your own, and there's always the biggest danger when you're revising, you didn't use the syllabus as a checklist. Okay, so coordinate bond, it refers to when only one atom donates both the electrons to be shared in a covalent bond. So in a normal covalent bond, you have one electron from each of the atom that, let me show you an example, it's better this way. If you have these and these, X and Y, so one of them give you one of these electrons and the other one will be the other electrons. So this is normal covalent bond. Whereas in a dative covalent bond, based on our definition, it could be X that has giving us both the electrons. So this is a dative covalent bond. So it is a covalent bond, but both the electrons in that covalent bond come only from one of the atom. So basically, only one atom donates both the electrons to be shared in a covalent bond. So this is just the I don't know, representation. It's not needed in your answer, as they are just asking for a 1-mark definition there. Now on to part 2, which is, well, basically I can just cross that out, I guess. Then I can just do my part 2 down there, since it's asking you about dot and cross anyway. So they're asking us to show the outer shell. So very importantly, they're asking us to show outer shell, electrons, and they're asking us to show CO. So if you look at it, you gotta show carbon as cross, oxygen as the dot. So let's have a look. Carbon, I usually like to draw this in terms of my Lewis diagram first. If we think about it contains a coordinate bond, so one of these bonds will be coordinate bond. Oxygen from 2 covalent bond happy. Carbon has 4 outer shell electron. I use 2 for bonding. I still have 2 more. Carbon is happy. Oxygen uses 2 out of 6 outer shell electron for bonding, so I should still have 4 more. Now let's just start counting. 1, 2, 3, 4, 5, 6. Carbon is not happy. Carbon is not happy here because carbon only has 1, 2, 3, and 4 original, 5 and 6. Oxygen is happy, 1, 2, 3, 4, 5, 6, 7, 8. So what carbon does is, carbon will want one of these 2 electrons to be donated from the oxygen. So now I have an arrow to show the dative covalent bond from the oxygen to the carbon. Around the carbon now, I have 1, 2, 3, 4, 5, 6, 7, 8, because in each covalent bond there are 2 electrons, so 2, 4, 6, and 8. So there's 8 electrons in the outer shell of carbon. Carbon is happy now. Oxygen, 2, 4, 6, and then 8. Oxygen is also happy. So this must be how the display formula. This is not dot and cross. This is the display formula where we show the bond as line. I always like to start from here because it's a lot easier to count, and therefore from here I can then convert into my dot and cross. So I have two remaining crosses on the carbon. I will have cross, cross, and then I have dot and dot. So these are the normal and normal covalent bond. And then this means from the oxygen to the carbon, so its dative covalent bond is got arrow. From the oxygen to the carbon, both these electrons come from the oxygen. So I've got a dot and a dot. Now I have oxygen. I still have two more dots because I have 6 outer shell electrons. I only use 4 for my covalent bonding, including 1 dative covalent bond or 1 coordinate bond. And that's it really for the 2 marks. Carbon is happy, oxygen is happy. That is how the dot and cross for carbon monoxide looks like. So we're still on question 2. Question 2C, they're asking us about ideal gas. So we have assumptions of ideal gas. So one of the most important assumptions, number 1, is definitely going to be negligible. So the gases have negligible intermolecular forces between them, between the molecule. So there are many other assumptions, but it's best to remember, at least 2 or 3, because in this case, they could ask you 2, they could ask you 3. It's very rare that they ask you all 5 of them or all 6 of them. First one is negligible intermolecular forces. The other one that I always remember is a perfectly elastic collision. Perfectly elastic collision between molecules. So meaning to say, your molecules, when they collide, there's no loss in energy. Collision with no loss in energy at all. So there's perfectly elastic collision. Of course, you can then think of any other assumption as well. So I'm just writing the third one out. We said there is the volume is so big because the gas molecules are so far apart, or the gas molecules or particles are so far apart that the volume is negligible. But that is not entirely true. It's only negligible relative to the volume of the container, because they are still contained within a specific container, and gas will fill up all the space available, which is the volume of the container. So out of the 2 most important assumptions, number 1 is definitely the most important one. Number 3 is actually pretty important as well, but sometimes we do include number 2 as well, because I personally just remember number 2 as one of the more important ones, but actually number 3 I just remember is actually quite important as well. There are other assumptions which I can't have it on top of my head at the moment, because I actually remember a couple of things at one time, this obviously being the most important one. Okay, so question 2, part C, and then number 2, why does N2 not behave as an ideal gas at very high pressure? So this is why N2 not very ideal, and this is at high pressure. So this is at specific condition. This question can also be changed. Why is it more ideal at low pressure? So we're going to think about what happened at high pressure. Okay, so at high pressure, your gaseous molecules, your N2 gaseous molecules are much closer together. They are kind of compressed in the space, are much closer together, and they are kind of squeezed closer together. Therefore, what happened is when they are closer together, they will have stronger intermolecular forces, because stronger intermolecular forces, which in the case of N2 is just stronger van der Waals, because it's a non-polar molecule between atoms of the same electronegativity, have stronger van der Waals between the N2 molecules since they are closer together. Intermolecular forces, the closer they are, the stronger is the van der Waals between the molecules, such that we cannot neglect them, such that we cannot assume negligibility anymore. We cannot assume them to be negligible. So basically what I'm saying is they become less negligible. Okay, I think that has gone a little bit bigger. Anyway, such that we cannot assume them to be okay, maybe I restructure my sentence. If the van der Waals gets stronger, therefore the intermolecular forces become less negligible. Intermolecular forces become less negligible. Sometimes as you write stuff, then you reread your sentence, they don't look so right, and that was one of the times. So I'm saying that after you write something, you should probably read it and try to make sense of it, see whether it makes sense to you or not. Okay, so I think that is when we can score 2 marks. I talk about what happens at higher pressure. They occupy smaller volume because they're much closer together. As PV equal to constant, so P increases, V will decrease, so you occupy smaller volume. In fact, they will also break one of these assumptions here. The volume is also becoming less negligible. The intermolecular forces also becoming less negligible, and therefore they become less ideal or does not behave as much ideal as you think they might do. Okay, I think I better start on a new page. Question 2C part 3. So what are they trying to do? Name all the type of intermolecular forces. Name all the type. So N2 and CO, so your intermolecular forces, name all the type. So I do have van der Waals for all of them, because both of them have electrons in the molecule. And then N2 is obviously non-polar. As you could see, presence of a dipole moment. Presence of dipole moment tell you is it polar or non-polar. So it's non-polar, so there's no permanent dipole at all. But there is permanent dipole in CO because it is a polar molecule. There is a presence of a dipole moment as they put a tick just above it. So just say complete this table, name. So just repeating the name, just van der Waals forces, which is your induced or temporary dipole there. The last question, which is part 4, they're asking you on why. Suggest why the bond in a molecule of CO contain a dipole moment. So carbon and oxygen obviously have different electronegativity as compared to nitrogen and nitrogen. They both have the same electronegativity because they are the same atoms, whereas here they are 2 different atoms, so they have different electronegativity. And since your entire molecule, let me spell this first, electronegativities. Is that correct? Electronegativity. Yep, okay. Since your whole molecule is just consisting of the bond itself, because there's just 2 atoms, and there's covalent bond between the 2 atoms, and the 2 atoms have different electronegativities, therefore, the bond is polar. Since the bond is polar, there is a dipole moment, and therefore, since the whole molecule just have this one bond, therefore, the whole molecule has a dipole moment. The whole molecule is polar. That's why you get permanent dipole. That's the end of that 13-mark question. I think we can move on to the next question now. Question 3. So this looks like organic chemistry, but not really. It's actually rate of reaction. So what do we have? We have 3 different temperature. So temperature in degrees Celsius in 20, 25, and also 35. So time taken for the reaction. So time taken for the pink color to disappear is 300 seconds there. Well, in second, and 65 and 20. So the question started out by talking to you about rate of reaction. And what we have is the reason why it is pink to begin with is because I have these 2 bromo, 2 methyl propane. So I have to draw out the structure. So it's 3 carbon there. I like to draw skeletal because it's beautiful and elegant and it's fast. So whatever you do, if you want to do well in A-level organic chemistry, try and master your organic chemistry by drawing skeletal formula again and again until you're good at it. Carbon form 4 bond, that is your important concept and a mantra that you have to keep on repeating and make sure you count things correctly. I label them with numbers because now I have 2 bromo. So I have a Br there, and I have a 2 methyl on this side as well. So I put bromo first because B before M. So 2 bromo, 2 methyl propane there. Okay, so this is the tertiary halogenoalkane. Tertiary halogenoalkane because the carbon bonded to the halogen is bonded to 1, 2, and 3 other carbons. So this is a tertiary halogenoalkane. You add this with NaOH aqueous in water. In water, you're going to do hydrolysis. So this is going to be hydrolysis, where you're going to substitute the Br with OH. So overall, it's a substitution reaction, like this. So this is the overall equation. But when you do the mechanism, knowing that it's a tertiary halogenoalkane, they will suggest to you if proceed via SN1, which is a 2-step mechanism. So a two-step mechanism would suggest that you have a double harm reaction profile diagram, and you proceed via a tertiary carbocation intermediate, which is kind of stabilizing to the tertiary carbocation due to the 1, 2, and 3 alkyl electron donating groups by inductive effect. So you can watch some other tutorial videos in my A-level concept playlist. As part of those electrophilic addition mechanisms, I explained the stability of carbocation as well. So yeah, I mean, I leave you to think about that on your own and to recap your stuff. But essentially what is going on then is I do have sodium hydroxide. Sodium hydroxide is alkaline or it's basic. And what I have is I have a phenolphthalein. So phenolphthalein is an indicator for acid-base reactions, but here I don't have acid-base reactions. I just have sodium hydroxide. It's alkaline, so phenolphthalein will be pink in alkaline solution. So when does the pink color disappear? The pink color disappear when all the sodium hydroxide is gone, meaning all the sodium hydroxide replaces the Br there, therefore there will be no more sodium hydroxide. That's when the pink color of the phenolphthalein will disappear, and that's when the reaction is finished, because there will be no more OH, no more OH minus, no more alkali in the reaction mixture, because the alkali OH minus we have gone to form the alcohol product. Okay, so this is the time taken for the pink color to disappear. So going back to the original question, part A, what is meant by the rate of reactions? So rate of reactions is referring to the change in the amount of a substance over time, over change in time. So it's actually the gradient. So when you think about it, so rate is also can be written as the change. So delta means change here. So change in the amount over change in time. So it's the gradient when you have an amount against time. Amount can be mass, amount can be concentration, amount can be volume. So all these things are something you have done as part of practical chemistry and the rate of reactions, hopefully. So part B is about a Maxwell-Boltzmann distribution diagram. So what do they want you to do? They're telling you that they give you all the labels for the graph. Let me just put in one of these graph here. So they have labeled this EA, and they have this as molecular energy. So usually I just label as energy, so energy on the x-axis, and then on the y-axis is what you call proportion of molecules with energy E. Okay, sometimes we just write it as N bracket E. It means the proportion of molecules or the number of molecules with energy E. This is at a particular temperature that is at 25 degrees Celsius. So this is energy distribution of that molecules of 2-bromo-2-methyl propane. So label the graph to show the proportion. So part 1 is label to show proportion of molecules that will react. So it's the proportion of molecules having energy greater than or equal to EA. So what I'll do is I will just shade this area, and then I will label this as part 1. Now use the same axis to sketch the distribution of energies at 50 degrees Celsius. So this graph is drawn for 25 degrees Celsius. Now I want to draw for 50 degrees Celsius. The graph will shift to the right, and then what happened then is this thing will be lower because there are more particles with higher energy, but then overall the number of molecules that you have doesn't change because you are just changing their energy. So at higher temperature, the graph will shift to the right. So your maximum, not higher E, but higher temperature. So more molecules have higher energy. Your graph will shift to the right. Your maximum number of molecules with the average energy will decrease because you are spreading out the molecules having higher proportions of energy. So as you could see here, the area under the graph would have increased as well. So I don't want to shade it, but this area there, together with this shaded area, there will be the total number of molecules with enough energy to react at the higher temperature. So this one is part 2 because this one is at 50 degrees Celsius. They give you 2 marks for that because you're supposed to get this right, where you shift to the right, so lower. And this one is supposed to be higher than this because there are more molecules having energy greater than or equal to EA to react. They haven't asked you to explain here, but 1 and 2 is done already. So I will probably just cross out number 1 there, and I'll just answer number 3 now. State the effect of an increase in temperature on the activation energy. So we have shifted the graph, but have we changed the activation energy? No effect at all, because activation energy of the original reaction will not be affected by temperature. In fact, you only get a new lower EA if you use a catalyst, but the catalyst does not change energy distribution, so a catalyst will not change the original distribution of energy. It will just give you a new lower activation energy. Anyway, they just want you to state the effect, so I just said no change, no effect there. Next question is on mechanism. So it's quite unsurprising that at least in a full AS paper 2 or paper 4, there must be at least one organic mechanism. So you can browse through my A-level concept tutorial playlist. I've got all the 5 or the 6 mechanisms that you're supposed to know in your whole of A-level. Most of that in AS, there's only one new mechanism in A2, is called electrophilic substitution. So browse through all of that, and yeah, you should hopefully master all of them, be able to draw them with your own examples again and again until you become familiarized with each of the steps. So here they have provided you with this partially displayed formula where they just show the tertiary halogenoalkane, because the carbon with the halogen is bonded to 1, 2, and 3 other carbon. So this is a tertiary halogenoalkane. The first thing I'll do is label dipole. Delta minus on the electronegative bromine, delta plus on the carbon there. Break the carbon-bromine bond, because tertiary halogenoalkane proceed via SN1. It's a 2-step mechanism. So the first step is the slow step. This is what you call the rate determining step, and you will get a tertiary carbocation. That's the very reason why it proceed via SN1, because tertiary carbocation is stabilized by 3 alkyl electron donating groups by inductive effect, stabilized by 3 times alkyl electron donating groups by inductive effect. So I like to label my mechanism with little things like this, because it not only allows me to recap my theory, it also allows me to explain why tertiary halogenoalkanes like to proceed via SN1 mechanism. So it's a 2-step mechanism. It's a tertiary carbocation intermediate. That's why it's a double harm reaction profile diagram. So this thing is not asked in this question, but you will have double harm reaction profile diagram. There's your reactant R, there's your product P, there's your carbocation intermediate there. So your carbocation intermediate is a slight dip, is a lower energy there compared to your transition state of that 2 individual steps. The second step will be fast, because then what happened is your hydroxide. Remember, you have sodium hydroxide. So you have your hydroxide as your nucleophile from the rich, which is from the lone pair. It will attack the poor. It doesn't attack the plus, because the carbon is the one that's poor in electron. The plus is a result of the carbon having one less electron. So you're forming the bond between oxygen and carbon, so from the rich to the poor. Okay, so what you get then is carbon, CH3, 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 OH. These are 2-dimensional diagrams. It doesn't really matter where you put the OH, could be there, there, or there. It's still going to represent the same thing. Of course, in 3 dimension, this should be a tetrahedral carbon with a 109 degree, so 2 flat, 1 in and 1 out from the plane. Anyway, this question is not asking you on 3-dimensional shape, so I'm sure you're alright there. So don't forget that you also have Br minus that you kick out from your very first step there. Okay, so that's it for this mechanism. I've included all the charges, all the dipoles, and all the curly arrows. I've included a little bit of extra information which are not required in this particular question, but they could ask you these in multiple choice. They could ask you these to explain in another kind of setting in the future paper 2 or even paper 4 for this A-level curriculum. So what's the name of this mechanism? So SN1 represents nucleophilic substitution first order. First order will make more sense in A2 rate of reaction, but SN refers to nucleophilic substitution. So the name of this mechanism is going to be nucleophilic substitution. I am not sure if they will accept SN2, but they did say name. So I think if you write down SN1, they will not really accept it because this is abbreviation. This is abbreviation and not the full name, and they're expecting the name of the mechanism. Anyway, onto the last bit of this question. It's a 2-mark question. So they say, repeat the experiment. Repeat. But instead of using the bromoalkane, you're going to use the... So this is your original experiment. Now you're going to use the chloroalkane, which is the 2-chloro, 2-methyl, propane. Predict the effect and also explain. So will the pink color disappear faster or will it disappear slower? This is about rate of reactions. We need to consider breaking the carbon Br versus breaking the carbon Cl. So I will first like to explain first. If I just go to my data booklet and I find bond energy, I want to locate the bond energy for carbon bromine as well as carbon chlorine. So carbon chlorine has a bond energy of 340 kilojoule per mole. Carbon bromine, which is actually a longer covalent bond because bromine is below chlorine. Bromine is a bigger atom than chlorine. Carbon bromine is a longer covalent bond than carbon chlorine, and therefore this bond is bound to be weaker. And in fact, that's the value given in the data booklet. It is a weaker covalent bond. You could have gotten it in the context of longer covalent bond due to the bigger size of bromine. Therefore, it's a weaker covalent bond since it's a longer covalent bond. Anyway, that is actually given in your, it's actually expected as part of your curriculum under covalent bonds, where students or candidates are expected to appreciate that longer covalent bond means weaker covalent bond because of the definition of covalent bond being the electrostatic force of attraction between this shared pair of electrons and the two nuclei. Okay, so I've talked about the bond energy. What we're doing is we are breaking it because we are doing hydrolysis, and our nucleophile is OH minus. Well, careful, negative charge on the oxygen. So our nucleophile is OH minus, and we need to break this CCl and CBr. So the CBr bond is weaker. So CBr covalent bond is weaker than CCl. Therefore, takes longer for CCl to hydrolyze, meaning to break. Okay, if it takes longer, that means the OH minus is consumed slower. So therefore, slower to consume or use up, slower to consume or react or use up the OH minus. So the phenolphthalein is your indicator as long if your OH minus is around for a bit longer, so it will take longer. So therefore, takes longer time for pink color to disappear. The pink color refers to the indicator. If your reaction is slower, so this reaction is slower since it takes longer to use up the OH minus due to the carbon chlorine bond being stronger. So the effect of using the chloroalkane is that it will take longer time for the thing to disappear. They want you to predict the effect and explain it. I always like to explain first and then predict or state the effect because I always find it the logical way of thinking is I can explain, then I can come up with the effect. If I come up with the effect first, I might then, muddle up my explanations and, fit in some wrong stuff in there just to fit the statement I will have made. So it doesn't matter as long as you got both points together. I know they want me to do two things. What happened to the rate to the time and explain the answer. I just decide to explain first and then state what happened to what happened to the time taken for that pink color due to the indicator detecting the amount of OH minus. How long will it take for that pink color to disappear? That's it really for the 11 mark organic question. So next up, question 4 is again another organic question. So question 4a part 1. We're going to complete the table by giving systematic name. So we need the name. So A, they give us the structural formula. If I just write down the structural formula, A is given as CH3, CH2, CH, CH2. Looking at that, you can see hopefully that this is the important carbon, 1, 2, 3, 4. You can try and go the other way, which is 1, 2, 3, 4. Then your alkene will be at 3, whereas in pink, your alkene will be at 1. So, you know, this one in blue is too high of a number for the important alkene. So it cannot be the one in blue, it has to be following this numbering. In pink, find the longest carbon, and you have 4 carbons, so it's got to be bute. It's got to be bute 1-in based on the structural formula. So this is based on this. We cannot tell whether, well, there's no cis and trans because you have a CH2 terminal group. You have 2 atoms. They are the same on the same carbon of the carbon-carbon double bond. So you can't have cis and trans. There's only one isomer of it. So this is the systematic name, or what they call the proper standard, whatever name you want to call it. Okay. On to the next one. So this is an isomer of it. So there's H and H there, a CH3 and a CH3. They have shown display like that. And if you compare that with C, C is going to be CC, and then the CH3 are on opposite side of that carbon-carbon double bond. So you could see that the CH3 are on the same side, the CH3 are on opposite side. So this is also butene, but here is 1, 2, 3, and 4. Here is also 1, 2, 3, and 4. So both of these is what you would call but 2-in, but then both of them are different. They are different in the arrangement of the atoms in space, even though they have the same structural formula, they have the same molecular formula. So these are the very definition of something called geometric isomer. Geometric isomers, or they come under stereoisomerism. The other partner in stereoisomerism would be the optical isomer, which these are not optical isomers, they are geometric isomers. Stereoisomers mean same molecular formula, same structural formula, but different arrangement of the atoms or the groups of atoms in space. They are on the same site, so this name is not complete without the cis. If you just write down but2-in, you don't get anything. If you just write down without the trans for the next one, you don't get anything as well. So trans but2-in means the CH3 are on the opposite side. Cis means they are on the same side there. Okay, hope that makes sense there. On to the very last one. So D, you have CH2 double bond C and then CH3 2. If you want, you can also sketch out like this, such as this. And what do we notice? We notice that let's number the carbon. So if this is 1, 2, 3, and of course then you could also do 1, 2, 3. Could you do the other way around? Okay, you could do the other way around. Let me do it in green. So you could do 1, 2, and 3. In both cases, your carbon is at 2, so it doesn't matter because you already minimized the let me see. No, actually the green is no good because with the pink, your alkene is at position 1. With the green, your alkene is at position 2. So the green one is not acceptable. We have to go for the pink one, where we will have pent. Oh, sorry, not pent, because this is 3. 3 longest carbon is prop, so it's prop 1-in. And I've got a branch, I've got a CH3 branch, so it's a methyl at position 2. So this is 2 methyl, prop 1-in. So if I just move that up there, so 2 methyl, prop 1-in, 3 carbon alkene, lowest number for the alkene at 1. And based on that numbering, the CH3, which is a methyl group, is at position 2. So that's the systematic name there. Incidentally, they asked me on the next part to explain stereoisomers. Well, I have done that previously, so I just need to, put it into words. So question 4a part 2, what is meant by stereoisomerism? So these are the kind of definition question which you cannot lose mark on. So basically, stereoisomerism refers to molecules or compounds having the same molecular and also structural formula. So the molecular and structural structural formula are exactly the same. And that is the very reason why you can't tell them apart by looking at structural formula. You can only see how they are arranged in space. So different, so what is different is different arrangement of atoms or groups in space. Okay, so it's to do with the spatial, or sometimes we say different spatial arrangement. I gotta write that down properly. Different spatial arrangement of blah blah blah, something like that. Okay, or you can say different arrangement of atoms or groups in space is exactly the same thing. Question 4, B part 1. So what do we have? We have W, which is an alkene C4H8. Now it reacts with HBr. You can get 2 possible carbocations. Carbocations means there are positive charges there's a positive charge on the carbon. So if you just draw out the other 2 there, so carbon there, it has a plus, it has a H, it has a CH2, CH3. Versus the other one, which is a carbon, a hydrogen, and then a plus. And what else? CH2, 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 CH3. If I just draw skeletal, because I love skeletal, 1, 2, 3, 4, so plus there. And then this one on the left is 1, 2, 3, 4, and then the plus there. So what you can see very clearly, hopefully, is the carbon with the positive charge there on the left is bonded to 1 and 2 other carbons. This is very clearly a secondary carbocation. Whereas the other one on the right, the carbon with the positive charge there is bonded to 1 other carbon. So this is a primary carbocation. You could of course also refer to what I've drawn on the top there, the carbon with a positive charge bonded to 1 carbon. Therefore, it's got 2 other hydrogen, since it is not it's got 2 other hydrogen because it's bonded to 1 carbon. I mean, in a carbocation, it's always going to be 120 degree carbon sp2 trigonoplanar, because that's just the way it is. In a carbocation, you have 3 bond pair and 0 lone pair on the carbon plus. So there is your valence shell electron pair repulsion concept from your AS shape of molecule. In this case, it's the shape of the ion there. What else? Let's say you get these 2. How in the world do you get these 2? Well, you can probably consider that it's going to be a straight chain. So W is a straight chain. So meaning to say between A, B, C, and D. So I'm not going to scroll back up. If you scroll back to the previous question, actually I can go through. No, actually I think it's better if I just sketch them out. So A is going to be this. B is going to be the cis, like this. C is the trans, and then D is just what is D? Like this. Okay, so looking at this, I can cross out D because D is branch. It cannot be C and B, because C and B you can never get the plus charge on the end. You see the plus charge there is terminal. It's at the end. It's at the end. Whereas here, your plus charge cannot be at the end, because as you add the H, because this is delta plus and the Br is delta minus, as you add the H, your plus charge will be there. It's not at the end. If you add the H there, the plus charge is there. It will not be at the end. Again, B and C must be out, because you want the plus charge at the end. We are just looking at option A. So the answer there must be, you just write down A. So W is A. Okay. Question 4, B part 2. So are they asking us a mechanism? No, they want skeletal. So finally, they purposely or they specifically ask for skeletal. Don't know why I put that in inverted. Skeletal, and they want major organic product. Major meaning you gotta get it from the more stable carbocation. So from the more stable carbocation. So we have written and we have drawn some of these carbocation in our previous page. I can just copy paste them, and that's exactly what I would do. So just copy paste it, but I can cut out all the unnecessary stuff like that, and like that. But I've already labeled the primary and the secondary carbocation. I explained the primary carbocation. The carbon with a positive charge is bonded to one other carbon. Here, the carbon with a positive charge is bonded to two other carbons, so it's a secondary carbocation. So what we can say is the secondary carbocation is more stable than the primary carbocation. And why is that? Because you have electron donating group. You have two electron donating group to try and stabilize this electron deficient center. And you only have one electron donating group to stabilize this electron deficient center there. So they want you to draw the skeletal formula of the major product. So number one, your major product is going to come from the more stable carbocation. So this is the more stable carbocation. So what I will get is I will get a secondary halogenoalkane, which is going to be that, and the Br. So what would the Br minus do? The Br minus basically attacks that carbon with a positive charge, and it will give you these 2-bromobutane. 2-bromobutane is the major product. They're not asking for the name of the product. They want the skeletal formula for the major product there. In terms of the explanation, how are you going to explain it? Let's see. Try to find myself a bit more space there. Okay, so why this is the major product? It comes from, so the major product comes from the more stable carbocation. So the major product is a result of a more stable carbocation intermediate, a more stable carbocation intermediate. So having stated that fact, so I can say that this thing here, or you can write down this thing which is given in the question. I just find skeletal formula a lot easier to use in my explanation. And who say you can't get marks, because you know this is perfectly exactly the same as that. It is the secondary carbocation. It has 2 times alkyl electron donating group by inductive effect. So inductive effect is a term stated in the syllabus under alkene chemistry, which is this bit actually, under electrophilic addition. Therefore, more stabilizing on the positive charge. More stabilizing on the positive charge than the primary carbocation, which is, well, this thing there. So this thing or this thing are exactly the same. I've just drawn it the other way around. 1, 2, 3, 4, 1, 2, 3, 4, positive charge at the end there. Okay, so you probably get 1 mark for this, and you get 2 marks for saying that why is it more stable than the other one? Secondary carbocation more stable than primary carbocation, because you have more alkyl electron donating groups by inductive effect. So which question are we on now? Question 4 still. So question 4, part C. You have propan-1-ol. So propan-1-ol is 1, 2, 3 like that. And you have consulfuric acid, and then you will get propene, and you will kick out H2O. So the consulfuric acid there is not a reactant, but what it does is it acts as a dehydrating agent. So the role there is as dehydrating agent. Okay, because you are removing H2O. This is actually the type of reactions is called elimination. The type of reactions is as stated in the AS Introductory Organic Chemistry. You call this as elimination. Dehydration did not appear in the type of reactions in the syllabus under Introductory Organic Chemistry. Be very careful there. Okay. So question 4, part D. We have alcohol Y reacts completely when you oxidize it with that acidified dichromate 6. So this is dichromate 6 is chromium plus 6 and is orange in color. And you will get Z, and when you get Z, there's the oxidation product. You will also get chromium 3 plus aqueous. This is chromium plus 3, and you get a green coloration as a result of the oxidizing agent doing its job and itself get reduced. Z is distilled, so this is heat and distill, meaning to say if you have primary alcohol, you can stop at the aldehyde. Most likely Z is aldehyde then, because of that information given about the distillation as it is being made, because aldehyde has a lower boiling point than the alcohol. If you can get aldehyde, this suggests that it must be primary alcohol since you can get aldehyde. So what is the type of reaction when Y reacts to form Z? Y reacts to form Z. This is in the presence of oxidizing agent. This is oxidation of the Y. You can call it redox as well, because in a way this undergo reduction, the alcohol undergo oxidation, so it is a redox reaction. It's just that when Y forms Z, so that is typically just what we call oxidation. I think redox is not appropriate. That occurs when Y reacts to form Z. When Y forms Z, that is the oxidation bit of the alcohol, definitely. But I think redox will be accepted because, like I said, what happens to the oxidizing agent as well. Identify a tick for the functional group present in Z. So we know that aldehyde also positive test with Tollens. Tollens reagent is basically silver with 2 ammonia, and this is colorless solution. So this is a colorless solution. It's got Ag plus 1. You get a silver mirror because this thing get reduced as the aldehyde get oxidized by Tollens. The Tollens itself get reduced back to silver 0. That's why you get silver mirror there. Anyway, so identify a tick with a functional group. So we're looking at aldehyde that's present in Z. So there's our tick, and that's it really. That's the end of that 12-mark organic question. Question 5. So very specifically, they say that S is a secondary alcohol, and it's got molecular formula C4H10O, which tells you the number of atoms in one single molecule. In part A, they want you to draw display. So if they want you to draw display, you got to show all bonds. One of the most careless mistake that students make is they don't show the OH. They don't show the OH like this because they show everything, but they forgot about this. Show all bond. If you make one mistake, you lose the marks. Okay. So secondary alcohol means the carbon bonded with the OH is bonded to 2 other carbons. Before doing this type of question, I will always just draw skeletal first. So this is 1, 2, 3. So this must be the, nope, there's no secondary alcohol because the carbon with the OH is bonded to 1 other carbon. This is actually primary alcohol. So this is not what I want. What do I want? That is 1, 2, 3, 4. This is also primary alcohol because the carbon with the OH is bonded to 1 other carbon. So this is not what I want. What do I want? Maybe 3 carbon. Oh, okay, I can see it. Put the OH here and put the methyl there, and I can have an OH there. And I have 1, 2, and 3. So not enough carbon. 4 carbon. So this is butane 2-ol. This is butane 2-ol. So this could be what I want. Once I get the skeletal, I can just convert that into display. So don't forget, display the OH as well, and then put in all the other hydrogen. Carbon form 4 bonds, so make sure that you count and you don't get any mistakes in this kind of question. 4 carbons, so CH3, CHOH, CHOH, CH2, and CH3. Okay. So question 5, part B, what do we have? S is converted. So S is your secondary alcohol. So it was 1, 2, 3, and 4. What happened in step 1? You are using PBr3, so that will convert the hydroxyl into bromide. So it just goes this way. As you can see, this was C4H10O. Remove OH, so you're going to lose the O, you're going to remove 1 H, you're going to get C4 H9Br, and that's exactly the same formula as given for T. So they say give the systematic name. What is the systematic name of T here? This is going to be 1, 2, 3, and 4. So systematic name for T is going to be 2-bromobutane. Anyway, so what is the type of reaction that occurs in step 1? So step 1, you have substituted the OH with the Br. So what is the type of reaction? They're not looking for mechanism, they're looking for the type of reaction as stated in the introductory organic chemistry of your syllabus. These are substitution because we have replaced the OH with the Br in this reaction with PBr3. Now moving on to question part 3, so it's step 2 already. Step 2 is basically converting that bromoalkane, that halogenoalkane, and I get U, and they say U is C4H9CN. You have replaced the Br with Cn. So it's going to look like this. You have replaced the Br with Cn. You have added carbon. So this is again another substitution. This is nucleophilic substitution for the mechanism. And for that reaction, you would definitely need, what do you need? You need your reagent, which is your KCN or NaCN, which is a nucleophilic source, K plus Cn minus or Na plus Cn minus, a nucleophilic source of Cn minus, and your conditions. These are very, very specific. You have to use it in ethanol. So this is your solvent, meaning you dissolve the KCN in ethanol, and you have to reflux them as well in order to get this reaction going. Last but not least, I'm running out of space there, doesn't matter. Let me just continue downward. So step 3, I add in some dilute acid, which could be dilute HCl or dilute H2SO4 or dilute HNO3. It's going to do acid hydrolysis of your nitriles. Hydrolysis is another type of reaction stated in introductory organic chemistry. So I hope you are aware of that. Don't know why my skeleton is very ugly there. Let me try and redraw that again. Try to draw trigonal planar for a carbon sp2 center. The Cn becomes CO2H. Nothing has changed in the back bonds 1, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, and 4. It's just this additional Cn that has gone to carboxylic acid there. So now when you have carboxylic acid, this is no longer 1, 2, 3, and 4. This is now the important carbon. So what we must do is we must put this as important carbon. So they become 1, 2, 3, and 4. So that's going to be 2-methyl butanoic acid, because it's a 4-carbon acid, it's butanoic acid, and it's got a methyl group at position 2. So they haven't asked us for the name of that product, but anyway, let's go to step 4 first. Step 4, they want us to complete the equation. So C4H9CN plus how many H plus how many water, and what is the product that we will get. Okay, I think it's best if I actually cut that and paste that to a new page. So okay, so this was question 5 part B. Let me just label it first. Remember just now we have our question like this, C triple bond N, and then that goes to carboxylic acid. So this was C4H9CN. So now this is going to be C4H9. Is it H9? Okay, so C4H9 refers to this thing here. So C4H9 refers to that thing there. And then I will have CO2H. So I maintain the same structural formula so that things are not confusing at all. See if I can move that a little bit there. So C4H9, CO2H. What else will I get? I'm doing acid hydrolysis. I will get NH4 plus because I will release ammonia actually. But ammonia in the presence of H plus will give me NH4 plus. Okay. Is that all? H2O. Okay, so I get the oxygen from the water. So I have 2 oxygen now, so I need 2 H2O. And will that be balanced now? So just looking at the Cn, the carbon balance out. The nitrogen, 1 nitrogen there. 4 hydrogen plus 5 hydrogen 1 plus 4 hydrogen is 5 hydrogen. 2 oxygens. I think this equation is balanced now. Let's just check the charge. No charge, no charge, no charge. Plus 1 and plus 1. This equation is balanced with 1, 1, 2, 1, and 1 there. We haven't reached the end of that question yet. So question 5, C part 5. So, oops, sorry, it's not part C, it's actually part B. We have an infrared spectrum, and actually that's the last 1 mark of this question. So you have unlabeled sample, S, T, or U. You look at the infrared. The infrared has no strong broad absorption at around 3000 to 3500. So that is usually where we look for the OH bond. So no strong broad absorption around that region means no OH. Okay. And then you look at around 1700. So no strong sharp absorption at around 1700 to 1800 wave number. This means no C double bond O. There is a very strange one at around 2200. So there is a strong, well, moderately strong and a sharp absorption at around 2200. So I don't need to write all of these down. These are what you are thinking in your head as you scribble through your spectra. You should be able to notice this straight away and come up with this conclusion just by looking at it, and you write down somewhere so that you're not confused. So S, T, and U. So if I go back to what I have just now, so S was your secondary alcohol, and then T was your bromide, and then U was your nitrile. Okay. Looking at these three, so I can definitely say the one with the OH is definitely not existing anymore because no OH. Can't tell between these two, but this thing definitely help. If you look at your data booklet under infrared, what do we have in infrared? You have C triple bond N, C triple bond N. The absorption from your data booklet, it shows at 2200 to 2250. Actually, they don't show it as strong, they show it as weak. Okay, that's what is stated in the data booklet there. So which means this thing there must be C triple bond N, and therefore I can rule out any other one. So in your answer, identify. Well, actually there's a lot of things they want you to do. So I already gotten this. So what do they want me to do? They want me to explain how this spectrum confirm the unknown sample contain U. Contains U. Well, okay. The spectrum has no absorption for OH at around 3000. What does it say in the data booklet? OH is around 3200 to 3600 wave number. Okay, and then how does this spectrum contains U? Also, there is C triple bond N absorption at 2200 wave number from the spectrum. What else? In your answer, identify one relevant absorption and the bond. So I identified the absorption, I identified the bond, and I said there's no absorption for OH. I can rule out this thing, and I can't be looking for this carbon halogen when I could already see that the C triple bond N is the absorption at 2200. So really, I mean, what am I doing? Hang on. Yeah, okay, so that one is all right. I want to cross out the number there. So this is what we are looking at here. That's it really for that 1 mark question. That's the end of that 8 marks last question actually in this paper 2. Yeah, so we reached the end, so don't forget to click the button on the bottom right to subscribe to the channel, and follow me at ptet.chemistry. That's at ptet.chemistry on Facebook, Instagram, and Twitter. And this is Dr. On signing off, and see you in the next tutorial video. Thank you for watching, and please share the channel widely with other people.